Hi, everyone, and welcome to Psych 3530. In this lecture, we will be discussing the repeated measures ANOVA, both the theory behind it, when we use it, why we use it, as well as the math of a repeated measures ANOVA. So, if you remember, last week, or in the last section of this class, we learned about one-way ANOVAs in which we have a between subjects design and three or more levels of the independent variable. So this would be group A versus group B versus group C. So maybe if you're doing a drug trial, a 0 milligram group, a 10 milligram group, and a 20 milligram group, where the independent variable, in this case dosage, is a between subjects variable, meaning that individuals only receive one level of the independent variable. However, this week we're discussing designs and then the statistic, repeated measures ANOVA, for a within subjects design that has three or more levels of the independent variable. So this is, we have a single group of participants, and then we subject that group of participants to at least three levels of the independent variable, and it's all the same group of people that we're following across each level of comparison. So this repeated measures ANOVA is analogous to our dependent samples t-test, except instead of just two levels of the independent variable, we're now going to have three levels. So that's basically what I just said here. The repeated measures ANOVA is a one-way ANOVA that's used to determine whether there are any statistically significant differences between levels of your independent variable across a single group of participants. So we no longer have group A, group B versus group C. What we have is a single group, and we give them treatment A, and then we give that same group of people treatment B, and then we give that same group of people treatment C. So it's a within groups design. It's an extension of a paired samples t-test where instead of two levels of the independent variable, we have three or more. This is going to occur in two major types of situations. The first is when participants are measured multiple times to see changes in an intervention or something that we're concerned about tracking over time. So we could think about time as the independent variable. Maybe we want to follow the progression of a disease. So we evaluate people at diagnosis, and then 1 year later, 5 years later, 10 years later, right, whatever the time frame is, we're taking a single group of people and then following them over time. So the independent variable is time, and our levels are the time frames that we choose. So you can think about this being used a lot in developmental psychology. Maybe we are developmental linguists interested in how children learn words. And so we follow a group of children from the age of 2 to 4 to 6, and we measure things like their vocabulary size. The key here being we have the same group of children that we're following over time. That's what makes this a within subjects design, and thus requires a repeated measures ANOVA. The other situation is when we don't use time as our independent variable. So we're not really following people over time, but we're repeatedly measuring people across different trials or conditions. So there's sort of a clue to the research design in the name of this statistic, right? Repeated measures. So we use this when we are repeatedly measuring people over time, whether that's a long stretch of time, like a longitudinal analysis, like our developmental psychologists studying vocabulary size, or whether we're simply exposing people to different levels of the independent variable, different conditions and trials sequentially really quickly. We're repeatedly measuring everyone. So here we'll sort of visualize the first scenario. We want to study blood pressure across 3 time points. Maybe we have given these people some kind of exercise or diet regimen. And so we measure their blood pressure at time point 1. And then they start doing our exercise and diet regimen. We check back in 6 months later with those same people and we measure their blood pressure. And then we check back in 6 months later and measure their blood pressure for a final time, such that we have the same group of people who we are following over time, such that our independent variable here is technically like time itself, right? The passage of time is kind of it can be considered an independent variable here. Versus situation 2, where imagine that you work for a Hostess, right? The company that makes the little cakes and bars and sweet treats, things like that. You work for Hostess, and Hostess wants to study how much people like its different flavored cakes. So you bring a group of people into a lab and you give them chocolate cake and you have them rate how much they like it. Then you give them caramel cake and they rate how much they like it. Then you give them lemon cake and they rate how much they like it. Notice how time isn't really the variable here. Like, this is all occurring like in one sitting in a laboratory at a single testing point. So we're not repeatedly measuring people over time, but we're repeatedly measuring people across conditions, such that our independent variable here is the type of cake that people are eating. And we take the same group of people and we give them each of our 3 types of chocolate cake, or each of our 3 types of cake: chocolate, caramel, and lemon. So we have 3 treatment conditions with the same group of people in each treatment condition. So in either of these situations, where we're following people across 3 or more time points, or when we're giving people 3 or more conditions or treatments in a single setting or a single time point, then we can use a repeated measures ANOVA. So just like the one-way ANOVA, a repeated measures ANOVA is an omnibus test, meaning it's going to tell us whether there's an overall difference. And then if there is an overall difference, we have to perform follow-up tests to tell us where specifically that difference exists. Just like with one-way ANOVAs, in a repeated measures ANOVA, our null and alternative or research hypotheses are going to always be the same, in that the null is that all of our groups are equal, and the alternative or the research hypothesis is that all of our groups are not equal with one another. And remember, when we say groups here, what we mean is treatment conditions, right? So the chocolate cake, the caramel cake, the lemon cake, right? It's the same set of people, but it's across treatment conditions. Just like before, we're going to use an F statistic. That's what we're going to end up working towards and calculating. We will again be partitioning variance in a repeated measures ANOVA, and we'll be taking a ratio of 2 of our types of variances. Again, don't worry so much at this exact moment about understanding what these things mean. We're going to go over that here in just a minute. But we're basically going to compare how much variability there are between our conditions, mean squared conditions. So that would be how different is the chocolate cake versus the lemon cake versus the caramel cake, or how different is time 1 versus time 2 versus time 3. How much variability is there in our conditions versus how much unexplainable error there is in the experiment. And that's really what makes this different from a one-way ANOVA. We're comparing the variance in our conditions to unexplainable error. And the utility of a repeated measures ANOVA is that we can estimate this unexplainable error with more accuracy than we can with a one-way ANOVA. And we'll discuss that here in a minute. So, just like with a one-way ANOVA, we break variance down into two types. Our between treatment or between conditions variance, that's easy. That's going to be our numerator. It's how much our levels of the independent variable differ from each other. Then we have our within treatments or within groups variance. This is how much variability there is within each individual treatment level. And with a one-way ANOVA, that's where we have to stop. We can only partition into two sources. But with a repeated measures ANOVA, we get some special abilities. We can further partition variance into subject level variability, and whatever's left over is error variability. So a repeated measures ANOVA takes the within treatments variability and it further divides it into subject and error variability. Now, what does that mean? Why does that matter? Why is that important? Let's take our time for a second and let's discuss it. So, first, we have this idea of total variability. Let's use the chocolate cake example as we walk through this. People vary in their rating of each cake, right? Some people like all cakes a lot. Some people only like some cakes. Some people are not going to like any of the cakes. Some people are going to have a bad day, and that's going to screw up their rating. Some people will have had cake last night for dessert, and that's going to maybe impact their ratings. There's just an almost innumerable number of places where we could get variability in people's ratings. People are messy. Right? Different people are going to rate the cakes differently for a whole host of reasons. So this is total variability. What kind of mood they're in, how hungry are they, physiological things like how many taste buds do they have. People differ in their number of taste buds. Personal preferences about flavors and textures, right? Any number of reasons why people might differ. We can divide that total global variability into variability that's due to changes in our conditions. So chocolate versus lemon versus caramel, right? If I have everyone's rating on chocolate and everyone's rating on lemon and everyone's rating on caramel, then I can get some idea about how do the ratings change based on the treatment or condition changing. So that's chocolate versus lemon versus caramel, right? That's easy to understand conceptually, right? Conditions variability or between conditions variability is the easy one to understand. We then have within groups variability. So within the chocolate group, people are going to differ, right? Some people are, let's say the cake was rated as a 7. Well, some people rated it a 7. Other people maybe rated it an 8 or a 9. Other people maybe rated it a 5 or a 6. Right? There's variability within the chocolate cake group. What a repeated measures ANOVA allows us to do is take that within groups variability and ask the question, of this within groups variability, how much is due to the subject variability? Think of this as individual differences. How much of this is due to individual differences versus how much is due to unexplainable error that we don't have a source for. So unexplainable error would be things like someone had a crappy day and they're just in a bad mood, and that bad mood is making them just sort of not care and wildly rate the cakes without really thinking about it. Right? We can't, as an experimenter, we can't control that. It's just unexplainable error that just finds its way into the experiment because humans are messy. Maybe there was something about if we have 10 people in a room, maybe one of them gets an old piece of chocolate cake, right? Just someone on the back end did a bad job. They gave them an expired, Hostess chocolate cake, and so that's just this random fluctuation of error that we didn't control for appropriately, right? That's going to be captured in the experiment, but we're not going to know where it comes from, right? We don't know that when we're looking at the data, but it's in the data. It's there, it exists, and it'll show up as random error variability. Versus subject level variability. So these are individual differences like Samantha hates cake, and so she rates them all as 2s, no matter what flavor they are. And Jose loves cake, and so he rates them all high, no matter what flavor they are. And Cynthia, likes some cake and doesn't like other cake, so her answers fluctuate across the flavors. There are individual level differences that we can tease out, and that helps us be more accurate in our estimates of the differences between our groups. So what's really happening here is that the ability to partition within groups variability into individual differences, and then whatever's left over is random error, is the mathematical advantage of our repeated measures ANOVA. Because if you work for Hostess, what you are concerned about is chocolate cake versus lemon cake versus caramel cake. That's what you care about. You don't care about Cynthia versus Jose versus Samantha, right? That's not the question you're asking. And so if what you can do is repeatedly measure these people over time, then we have data on their individual differences between each other, and we can mathematically partition out those individual differences and, in a sense, throw them away. We throw them in the trash because I don't care about Samantha versus Jose versus Cynthia. That's not my question. So if I can quantify those individual differences and then trash them, I'm left with a more accurate mathematical understanding of my question. And my question is chocolate versus lemon versus caramel, right? That's conditions variability. That's what I care about. And so if I can throw away this unwanted individual subject variability, then I'm better for it. So what we actually see is that a repeated measures ANOVA is mathematically preferable to an independent or one-way ANOVA. Mathematically, we would always prefer the repeated measures ANOVA because it allows us to throw away individual level variability because I have information about each individual multiple times, right? I've repeatedly measured the same individuals multiple times, so I can mathematically assess their individual differences from one another. There will always be this random error variability. There's nothing we can do about that. It will always be there. But what we're doing is we're making our F statistic stronger by throwing away the individual level variability. How does this make our F statistic stronger? This is the same sort of chart that I've just sort of made to walk through as is here. So it makes the F value stronger because our conditions variability, right, our between treatment effect, becomes the numerator of our F ratio. It's the numerator of our F statistic. In a one-way ANOVA, the within treatments variability is the denominator of our F statistic. But we're not doing a one-way ANOVA, we're doing a repeated measures ANOVA. So we split the within treatments variability into individual differences between subjects variability and error variability. As we said before, we're not interested in individual differences, so we throw that away. We get to remove it from the experiment. And then the denominator of our F ratio is what's left over as our error variability. So what this is going to do is it's going to make our denominator smaller, a smaller value than had we conducted a one-way ANOVA. Because remember, this would have been our denominator for a one-way ANOVA, but I got to split it into individual differences and then pure error. I get to throw away the individual differences and use only what's left over, which is error variability, as the denominator of my F ratio. So in a repeated measures ANOVA, the denominator of the F ratio will always be smaller than had we done a one-way ANOVA. And that's the power, the mathematical power of using a within subjects repeated measures design. Because if my denominator is smaller, then what happens to my F ratio? It gets bigger, right? The fraction gets bigger if my denominator is smaller. And so when that happens, we have more statistical power. And so it's easier to find significant differences in a repeated measures ANOVA when compared to a one-way ANOVA. Okay, so here we have a few slides. I'm going to buzz through them because this is everything that I've just sort of explained to you. It's just written out because I know it's a lot of information. And so I want you to be able to go back and listen to this as well as read it if you need to, in order to understand, what is this between treatments variability? What does within treatments variability mean? What does it mean to divide it into two sources? What are these two sources and why are they important? So those slides just sort of go through and spell out in words all the stuff I just said in case you need to sort of read through it and take your time visually. Okay. So the way that this works mathematically is that, and don't worry if you don't know what any of these letters and stuff mean. We're going to break this down one step at a time. Each of these sources of variability, so total variability, between treatments variability, within treatments variability, individual difference variability, so between subjects variability, and error variability, all end up with a sum of squares. So we end up with 1, 2, 3, 4, 5 sums of squares. And each of them has a formula. And so we're going to go through and learn how to calculate each of those sums of squares. Each of those sources of variability also has a degrees of freedom. So we're going to go through and learn how to calculate each of those degrees of freedoms, or degrees of freedom. And then we simply fill out a table, an ANOVA table, with each of our sources of variability, each of our degrees of freedom, and then we use those numbers to eventually calculate our F statistic. Okay. So let's run through an example. Now, before we start this is sort of new mathematically. So I'm going to give you a couple points, a couple places in this lecture to hit pause and take a step back and look at things, practice the math maybe on your own, and make sure you've got it right. So I'll give you sort of a command to pause on occasion. Take that as an opportunity to just do some of the work yourself and make sure you've got it, run through it, and before we move on to the next point. So our research question: Dr. Ash is testing a new treatment on long-term pain of 4 back surgery patients. Given the data below, does this new treatment reduce back pain over time? Alpha equals 0.05. So we always express our hypotheses as non-directional. The null is that there will be no change over time. Notice that we have 4 participants, participant A, B, C, and D. We're going to measure them at 4 time points. Before the treatment, what was their pain level? 1 week after treatment, what was their pain level? 1 month after treatment, and 6 months after treatment. So, sorry, this should have like a 4th one, but you get the idea for the hypotheses. They're all either are null is that they're all equal. The alternative hypothesis is that there's a difference somewhere, right? They're not equal. So, given the data below, does this treatment reduce back pain over time? So we have an example here of a longitudinal experiment where we are following people across 6 months after their treatment, and we're repeatedly testing them and getting data on their back pain. So before we start, make note of this table. This is the type of thing that you will need to set up in order to appropriately mathematically conduct a repeated measures ANOVA. I will be posting a blank one of these on iCollege so that you can print it off and use it when you do practice problems, when you do the homework, and when you take the exam. So for now, draw this out on a piece of paper as we're going through this and doing this example, but know that you will have a blank version of this that you can use at any point moving forward. So we have a lot of stuff going on here. We'll take it piece by piece. First, we want to list all the data for our participants. So we have our 4 participants. So person A had an 8 before treatment, a 2 1 week later, a 1 month later, and a 1 6 months later, right? So person A, we list their data with our treatment conditions along the top. Then we list person B's data, person C's data, and person D's data. Next, we're going to have a few calculations per treatment condition. We're going to have a T1, which is the sum of all scores in the first treatment condition. Then a T2, the sum of all scores in the second treatment condition, so on and so forth for each of our treatment conditions. So we'll have 4 T's, where T is the sum of each treatment condition. We'll then have an M, which is the mean of each treatment condition, right? That's easy. That's just the sum divided by 4 participants. Then we'll calculate a sum of squares for each treatment condition. So we're going to do a sum of squares table for before treatment, a sum of squares table for 1 week, a sum of squares for 1 month, and a sum of squares for 6 months. We're then going to calculate a standard deviation for each of those treatment conditions. Then over here on the right, we're going to have our P's. We will calculate a P for each participant. P is the sum of all scores for that participant. So person A, what do they sum to? Person B, what do they sum to? Person C, what is their sum of scores? And person D, what is their sum of scores? So we're going to be using the t's and our sums of squares to calculate our between conditions variability, right? That's the effect of the condition, which in this case is time. We're then going to be using our p's to calculate our individual differences, which is what we get to throw away, right? That's the advantage of the repeated measures ANOVA. We then need to note a few things. Little n is the number of participants in a single group or in a single treatment condition. So here we have 4 participants in each treatment condition, right? They're the same participants, right? We're following them over time. So little n is 4 because there's 4 data points in each treatment condition. K is the number of treatment conditions, the number of levels of our independent variable. So K is 4 as well because I have 1, 2, 3, 4 treatment conditions. Big N is the total number of data points. So in this case, I have 4 participants, each providing 4 data points. So big N is 16. And then G is the sum of all my data points. So you can also get G by summing your T's, right? Because if G is the sum of all data points and T is the sum within each treatment condition, then I can just sum my T's to give me G. So what we do is we walk through and we do each of these calculations. So first, let's start with our T's and our P's. The sum of treatment condition 1 is 26. So person A plus B plus C plus D. We do the same thing for week 1. We do the same thing for 1 month. We do the same thing for 6 months. And we can see here that pain decreased over time, right? Total pain, quote unquote, for our 4 participants was a 26 before treatment. And by 6 months, total pain is only a 4. So it looks like the treatment is working. But our question is, how has the treatment worked over time? So what the repeated measures ANOVA is going to be able to do is compare these individual comparisons if the overall ANOVA is significant. Right? We'll need to do Q tests again. Then what we've done is we've summed each participant, our P's. So I took participant A and I summed all of their scores to 12. Participant B summed to 6, C summed to 10, and D summed to 16. So that's step 1. Sum your T's and sum your P's. So press pause, take a look at that again, make sure you can do it correctly. Okay. The next step is that we calculate a mean, and then we do a sum of squares and a standard deviation for each treatment condition. Now, I've glossed over a lot here because you should know how to do a sum of squares table by this point in the semester. Finding the mean is easy, right? We add up all our values, we divide by how many there are, so 4. So 26 divided by 4 gives me an average pain score of 6.5 for before treatment, an average pain score of 2 for 1 week, an average pain score of 1.5, and then an average pain score of 1 for 6 months. So now take each of these means and then its data from its treatment condition and calculate the sum of squares for each treatment condition using its own mean. So that means 4 in this case, sum of squares tables. So a sum of squares table for before treatment, a sum of squares table for 1 week, a sum of squares table for 1 month, and a sum of squares table for 6 months. So go ahead and press pause. Make sure that you can calculate those 4 sum of squares tables and that you get these numbers. 11 is the sum of squares for before treatment. 2 is the sum of squares for 1 week, 9 is the sum of squares for 1 month, and 2 is the sum of squares for 6 months. So hit pause. It's going to take you a few minutes to do this. Hit pause, calculate your sum of squares, make sure you can do them correctly, and then come back to the lecture. Okay, so now that you have your sum of squares, it's just 2 quick steps to get your standard deviations for each group, right? You take the sum of squares, you divide by n minus 1, and then you take the square root. So 11 divided by 3, and then you take the square root. 2 divided by 3, take the square root. 9 divided by 3, take the square root. 2 divided by 3, take the square root. Gives you your standard deviations. Go ahead and do that. Hit pause and come back to me when you're done. Okay, so now we've got a big step done here. A big chunk of this is finished. We can fill in our N, K, big N, and G relatively quickly. So little n is the number of data points per condition, so 4. K is the number of treatment conditions, so 4. Big N is the total number of data points. So I have 4 people across 4 treatment conditions, so 4 times 4 is 16 data points. And then G is the sum of all scores, so the sum of all my data. You can also sum your T's in order to get G of 44. Okay. Now we are ready to start partitioning our variance into each of these sources. These formulas look a little goofy. They take a little bit of time, but we're going to take them one at a time, step by step, and we're going to break them down. They're not mathematically difficult. Nothing about this is anything beyond basic algebra. But we have to be very careful, lots of attention to detail, and we need to follow order of operations correctly in order to do our math right, because there's a lot going on here. So in our next steps, you need to keep in mind that staying organized in your math is really, really important. Try not to just scribble numbers all over the page. Stay organized, because staying organized is really going to help. Okay. So we took each of these formulas and we've listed it as a source of variability. So we have a sum of squares for between our treatments, a sum of squares for within our treatments, a sum of squares for our between subjects variability, sum of squares for our error variability, and then our total sum of squares. So we're going to use these formulas and the data from this table to complete this second table, which you'll also have a blank copies of that you can print out. And this is the table that's going to get us our F. So we have a multi-step process here. I call this the T and the P table. Our T and P table get us ready to calculate our sources of variance. So that's step 1, to fill out the T and the P table. Step 2 is to use the T and the P table to fill out our sources of variability table, which is where we're going to calculate our F. So let's take these one at a time. We'll go with between treatment conditions first. The formula for the sum of squares of between treatment is that we take the sum, that's what this guy stands for, the sum of every t squared divided by little n. So we're going to take every t, so t1, t2, t3, and t4. We're going to square every t. We're going to divide by little n, which was 4. And then we're going to sum every t squared divided by 4. So 26 was t1. So we take t1, say 26 squared, and we divide by 4. That gives us 196. Then we take our second t, which was 8. We say 8 squared, then we divide by 4, and it gives us 16. Then we take t3, which was 6 squared, then we divide by 4 to get 9. And then our final t, 4 squared, divided by 4 to get 4. So we took every t. So here are our t's. 26 was t1, 8 was t2, 6 was t3, 4 was t4. We took each t and we squared it. Then we divided each t squared by little n, which in this case was 4. So we do each of those calculations independently. T squared divided by n, number 1. T squared divided by n, number 2. T squared divided by n, number 3. T squared divided by n, number 4. And then we're going to sum those 4 values. So 169 plus 16 plus 9 plus 4. So go ahead, press pause, and make sure you can do that, and you know where those numbers are coming from. We're then going to take this sum of these numbers, and we're going to subtract by g squared divided by big N. Sorry, that's a subscript there. That should be above the 44. We're going to take g squared, and we're going to divide by big N. So we already found g squared. This basically becomes a reference table, right? Once we've calculated everything here, we're just pulling these values over as we need them. So we've already calculated g. So we just square g, so 44 squared, divide by big N, which we already found was 16, total number of data points. So 44 squared divided by 16 gives us 121. So that's the right side of this equation. So we go 169 plus 16 plus 9 plus 4 minus 121 gives us a sum of squares between of 77. So that's going to go up there. So all that to fill in this one box. The next box is our variability, our sum of squares within each group. This one's easier because we've already calculated the sum of squares inside of each treatment condition. Right? We have our sum of squares for treatment 1, our sum of squares for treatment 2, treatment 3, and treatment 4. So if I want to know the total amount of variability within my treatment conditions, which is what this is, then I just take each sum of squares and I sum them, right? That's what the sum of every sum of squares inside of each treatment. So my 4 treatment sums of squares, 11 plus 2 plus 9 plus 2 gives me 24. We now have another sort of long one because we have to fill in this next box, which is our individual difference sum of squares. That looks very similar to the first step, the sum of squares between. But instead of t and little n, we have p and k. P and K. So it's the sum of every P squared divided by K. So we're going to go back and we're going to pull our P1, which was 12, our P2, which was 6, our P3, which was 10, and our P4, which was 16. We already found our P's here. We pull each of those P's, we square them, we divide by 4, and then we write down that number. So P1 squared divided by 4 is 36. P2 squared divided by 4 is 9. P3 squared divided by 4 is 25. P4 squared divided by 4 is 64. So it's the same thing that we did over here, except instead of T and N, we use P and K. So go ahead and press pause. Make sure you know where those numbers are coming from. Every P squared divided by 4. Okay. So we sum all of those values, 36 plus 9 plus 25 plus 64, and we subtract by the same thing that we subtracted over here, G squared divided by big N. So we already have G squared divided by big N, right? We already have this term. It was 121. So we can say 36 plus 9 plus 25 plus 64 minus 121 gives me 13. Let's not lose sight of the importance of this number. This quantifies the variability that's due to individual differences. I don't want that variability. What I want is the variability that I can't explain, right? That's my point of comparison. The variability that I can't explain, that's error variability. So what we do, because individual level or subject level and error variability are my two components of within groups variability, I'm going to take 24 minus 13, and it gives me 11. So I end up with 11 sum of squares for my error variability. And then for sum of squares total, we, sorry, I've got a little mistake here. We add up all the sum of squares in the table, but I'll fix this on the static lecture, my bad. But so we add up all the sum of squares in the table, but keep in mind, and this is the mistake I made, that subjects and error variability are the two components of within subjects variability. So, this 13 and 11 are what make up this 24. So you don't want to do what I did, which was add them all together. What we want to do is add up the sum of squares between, which is 77, plus our within groups sum of squares, which was 24. 77 plus 24 does give us 101. So this number is correct. I just accidentally mistakenly added in plus 13 and plus 11, right? So we want to add 77 plus 24. So between treatment conditions and within treatment conditions, 77 plus 24 gives us 101. Okay. The hard part is over, I promise. That is the extent of our sort of difficult computations here. Because the next piece is filling out our degrees of freedom for each of these sources of variability. These degrees of freedom will be given to you, right? You don't have to memorize these. And so we just go through and we calculate each one. So degrees of freedom between is K minus 1. Right? So here are the formulas for our degrees of freedom. K minus 1, K was 4. So between degrees of freedom is going to be 3. Within degrees of freedom is big N minus K. So big N was 16. That's how many data points I have. Minus K, which is my number of groups, 4. So degrees of freedom within is going to be 12. My between subjects degrees of freedom, my individual difference degrees of freedom is little n minus 1, so 3. My error degrees of freedom is the degrees of freedom within minus the degrees of freedom from the subjects. So big N minus K minus little n minus 1, right? Just like we did with the sum of squares, right? Within minus subjects, it's the same thing for degrees of freedom. Within degrees of freedom minus the subject degrees of freedom. So 16 minus 4 was 12. 12 minus 4 minus 1, which is 3. So 12 minus 3 is going to give me 9 error degrees of freedom. And then degrees of freedom total is big N minus 1. That's 16 minus 1. So we can put all those there. If that's confusing, press pause, or you need to go through and make sure that you know where all these numbers are coming from. Go ahead. These numbers, K, big N, little n, right, all that's coming from our T and P table. So make sure you know where you're grabbing those numbers from and that your answers match these degrees of freedom. Okay. The next step is we need to calculate our mean squared. That's MS. We're only going to do a mean squared for between and a mean squared for within. Our mean squared between treatments is equal to the sum of squares between treatments, so 77, divided by the degrees of freedom between treatments, 3. So 77 divided by 3 is going to be our mean squared between. And remember, in a one-way ANOVA, we would be using within, but that's not what we want here because we're going to throw away the variability due to subjects, and we're going to use what's left over, which is our error variability. That's what we want to use for our denominator, mean squared. So I'll say that again. In a one-way ANOVA, we would be using 24 divided by 12 because that would be all that we can do. But because we have a repeated measures ANOVA, it allows us to subtract out the subject level variability. We're going to throw it away. And so we're going to calculate our mean squared with the error variability. So we do the sum of squares error, which was 11, divided by the degrees of freedom error, which was 9, to give me 11 divided by 9 for my mean squared. So 77 divided by 3 up here, 11 divided by 9 down here. We just divide across the table in only these two. We only do it for between and error. You don't need to do it anywhere else. So our mean squared for treatment conditions is 25.67. It's 77 divided by 3. And our mean squared for error is 1.22. 11 divided by 9. And so then we're one step away from our F value. Our F is the mean squared of conditions divided by the mean squared of the error. So 25.6768, right? Rounding can be an issue here. Divided by 1.22 equals 21.04 for an F. Again, if you're a little off, if you've got 21.01, 21.06, 21.07, that's all perfectly reasonable and within random error variability or random rounding variability. Okay, so we finally have our F value after all of that. If you need to review that, if you need to press pause or you need to go back and replay some of this, please do so. But that's computationally the most difficult part of this. We finally have our F value. Okay. Now, just like with our t-tests and just like with our one-way ANOVA, we need to know, is this F value significant? So we use our degrees of freedom that we used for our mean squared. So we use our between subjects or between conditions and our error degrees of freedom to find our critical value on our F table. Here we see our F table. These are posted on iCollege. We want to snag the one for 0.05 because that's what our alpha was for this practice problem. So we have our numerator degrees of freedom, right? That's why it's called the numerator degrees of freedom, because this degrees of freedom contributes to the numerator of our F value. Numerator degrees of freedom was 3. That's our between conditions degrees of freedom. Our error degrees of freedom was 9, which gives us a critical F value of 3.8625. Our F value was 21.04. Our critical value was 3.8625. Because our F value is greater than the critical value, we reject the null, and we're going to conclude that, let's not forget what our example was here, that pain does change over time. Pain changes over time. That was the question. And we found, yes, that over time, across our treatment conditions, pain significantly changed. That's what this tells us. We have a large F. It tells us that pain significantly changed over time. This tells us that there's a main effect of the independent variable, but it doesn't tell us where that difference exists. Just like with a one-way ANOVA, we need to calculate post hoc tests, and we also need to calculate the magnitude of our effect size. So we're not quite done yet. Because this is significant, we have 2 more steps. If this result was not significant, if our F value was less than the critical value, then we would stop. We would actually be done because it's not a significant result. Nothing happened, right? Time did nothing for pain. But we found that something happened. Right? A difference exists. So we need 2 more steps: post hoc tests and an effect size. Let's tackle the easy one. The effect size, that's eta. We call this eta squared. The effect size is our sum of squares between treatments divided by our sum of squares total minus the sum of squares between subjects or individual differences. So we go back to this ANOVA table. We pull the values we need. We need between treatments sum of squares. We need between subjects sum of squares, and we need total sum of squares. We pull those values. We get 77 divided by 101 minus 13 to give us 0.88. That's our effect size. Easy peasy. Next, we need to run what are known as Tukey post hoc tests. This is basically another Q that we're going to calculate, just like we did with our one-way ANOVAs. And just like with one-way ANOVAs, we calculate a Q for every possible iteration of a comparison of our independent variable levels. So here we had 4 levels: right? Before treatment, 1 week after treatment, 1 month after treatment, 6 months after treatment. So we actually need 6 comparisons because I have level 1 versus level 2, level 1 versus level 3, level 1 versus level 4, level 2 versus level 3, level 2 versus level 4, and level 3 versus level 4. 6 total comparisons, right? Every possible comparison across 4 groups. I like to set up another little table to make it easier because a Q, or what we're going to call here our Tukey score, a Q is the mean difference between these 2 groups. So the mean of group 1 minus the mean of group 2. The mean of group 1 minus the mean of group 3. The mean of group 1 minus the mean of group 4, right? So 1 minus 2, 1 minus 3, 1 minus 4, 2 minus 3, 2 minus 4, 3 minus 4. Go ahead, go look back at your T and your P table. Pull all of your group means or the treatment means, and you find your mean differences. Those all become the numerators of your Qs, and we're going to list them here. So the mean of treatment 1 minus the mean of treatment 2 was 4.5. The mean of treatment 1 minus the mean of treatment 3 was 5. The mean of treatment 1 minus the mean of treatment 4 was 5.5. The mean of treatment 2 minus the mean of treatment 3 was 0.5, so on and so forth. Press pause, go back and grab those treatment means from your T and P table, and make sure you know where these mean difference numbers are coming from. So go ahead and do that. And now that you're back, we can calculate the denominator for each of our Qs. The denominator is always the same for each of our comparisons. So this is a little easier. We just need to do one calculation. The denominator of our Q is the square root of the mean squared error that comes from our ANOVA table divided by little n, which was 4. So the mean squared error, I believe, was like 11. No, I'm sorry. The mean squared error was 1.22. So we take 1.22, divide by little n, which was 4, and then we take the square root of that, and we get 0.56. So 0.56 becomes the denominator for each of our Qs. Make sure that you know where that number is coming from. Go ahead and take a second if you need to pause and do that calculation for yourself. So now we have what we need for our 6 Q values. These are 6, think of these as 6 separate fractions. We have each numerator, and then we have each denominator. So then we just divide down, and we get our Tukey Q scores for each of our comparison points. So 4.5 divided by 0.56 is 8.04. 5 divided by 0.56 is 8.93. 5.5 divided by 0.56 is 9.82, so on and so forth. So we get our 6 Tukey Qs. Now we need a critical Q value. We are going to use degrees of freedom error and K to look up our critical Q value on the Q table. Your Q table is posted on iCollege as well. We have number of treatments, K across the top, that's 4. We have degrees of freedom for the error term along the left-hand side, that was 9. The top value corresponds to 0.05, the bottom value to 0.01 in each box. So we need the top one because alpha was 0.05 in this example. 4.41. So we have our 6 Tukey Q scores. We have our critical Q value, which is we're comparing it to. So now we need to know which of our 6 comparisons was statistically significant, meaning which of these Tukey scores is larger than our critical Q value. And we find that the first 3 are the only ones larger. So let's take a step back and think about what we've done so far. We calculated an overall F value that told us there's a significant difference somewhere. Somewhere a significant difference exists because our F was statistically significant. So we're conducting a study on back pain across time, before treatment, 1 week after treatment, 1 month after treatment, 6 months after treatment. That's 1 through 4. Because our F was statistically significant, we conducted Qs, what are known as Tukey post hoc tests. We conducted Qs in order to evaluate each individual comparison of the levels of our independent variable, or our time points. And we found that the true difference exists in only 3 of those comparisons: 1 versus 2, 1 versus 3, 1 versus 4. So now we have to do a little bit of conceptual work, because we have to think about, what does this mean? So our first treatment condition was the before treatment, right? What was pain before treatment? It was an average of a 6.5. Our second condition was, what was pain after 1 week? It was a 2. What was pain after 1 month? It was an average of 1.5. What was pain after 6 months? It was an average of 1. We just found that the only significant comparisons are 1 versus 2, 1 versus 3, and 1 versus 4. So if 1 versus 2, 1 versus 3, and 1 versus 4 are significant, what that means is that 2 versus 3, 2 versus 4, and 3 versus 4 are not significant. Basically, what we have found is that pain does not differ between 1 week, 1 month, or 6 months after treatment. Pain stays the same from 1 week all the way to 6 months, right? Because none of these comparisons were significant. What was significant was before treatment compared to every other time point. Each of those comparisons were significant. So what this means is that before treatment had higher pain scores, right? The mean is higher. Before treatment had higher pain scores than all other time points. What I suggest doing is sketching out just a quick little graph to help you see what this means. Right? We took the mean of each condition, and we just did a quick little graph where we put our condition on the x-axis and our pain score on the y-axis. So we can see that that 1 week, 1 month, and 6 months are all basically the same, right? Pain doesn't change across 1 week, 1 month, and 6 months. And that was reflected in our Qs, right? Those comparisons over here, 2 versus 3, 2 versus 4, and 3 versus 4, were not significant. What was significant was group 1, or treatment 1, compared to all the others. Before compared to 1 week, before compared to 1 month, before compared to 6 months. So what we should conclude is that the treatment works immediately and then continues to work in the same way for the next 6 months. That's the conceptual take-home message that we want here. That immediately after receiving the treatment, right away, pain goes down, and then pain stays consistent over time. So the treatment works immediately and has a long-term effect on pain. And so all we have left to do, finally, is write up our APA-style conclusion. So repeated measures ANOVA was conducted to assess the impact of treatment over time for back pain. That's our test and our research question. A significant difference was found over time in ratings of pain. F, 3, 9, those are our degrees of freedom we used. 3, which was between treatments degrees of freedom, 9, which was error degrees of freedom, equals 21.04, that was our F value, MSE, mean squared error, equals 1.22, that was the denominator of our F value. Eta squared, which was our effect size, was 0.88. P was less than 0.05 because we were significant, and that was our alpha. Then, Tukey post hoc tests revealed that pain ratings prior to treatment, which had a mean of 6.5 and a standard deviation of 1.91, were greater than all other later time points, whether they were 1 week with mean and standard deviation, 1 month, mean and standard deviation, 6 months, mean and standard deviation, which did not differ from one another. So here in this segment, what we do is we explain the results of those Q values. So the first thing we do is what test and what was our research question. The second thing we do is the statistics for our overall ANOVA. If we're significant, then the third thing we do is we explain which of our post hoc tests were statistically significant and which were not. And then we provide our take-home message, our conceptual take-home message, which was that treatment for back pain works immediately and then stays consistent over time. Thus, treatment has an immediate and long-term reduction in back pain that does not vary over time. That's our take-home message. So I know that this was a lot. I know it's lots of steps. It's lots of new stuff. It's lots of new math. Go back, rewatch this, redo the practice problem, and make sure you understand where everything is coming from. And then here I have our first practice problem, another problem for you. Here we have the research question. We want to see if 3 professors vary in the difficulty of their exams. This one, I'm not really going to do too long of a voiceover. I'm just going to kind of walk through the slides here really quickly. What I've done is just filled out all of the numbers, all of the calculations for you. What I want you to do before you move on is first rewatch the problem if you need to watch this problem. Second, take a crack at this practice problem and see if you can, using the steps that we previously saw, get these numbers. I'm walking through them fast here. Obviously, you're going to have to sit and do the math and do the calculations. And what we find here, because I want you to see this example, is that we have a very small f value, 0.29. Again, make sure you can do this math. Don't take this for granted. Go back and do all these calculations. We have a very small f value for this problem. We're going to find our critical f. Right? It's going to be bigger than our calculated f value. The critical f was 7.559. Bigger than our calculated f value, which means we are not significantly different. Nothing happened here. Our research question was, do the professors vary in the difficulty of their exams? We had 3 professors. And so we're going to conclude that the professors do not vary in the difficulty of their exams because the f, our calculated f, is smaller than our critical f. So there's no significant difference between the professors. And so we don't have to do anything else. There's no Q's, there's no eta squared. You don't have to do this difficult conceptual interpretation of what's going on because the professors do not differ. So your APA style conclusion gets much more simple. Repeated measures ANOVA investigated whether 3 professors differed in the difficulty of their exams. There were no significant differences between the exam scores. Here we have our statistical statement of our overall F. It was not significant. Thus, the professors do not differ in the difficulty of their exams. So, go redo the original problem. Make sure you understand it. Use this first practice problem to make sure that you can do the math and that you can do all of these steps to get to your F. We found a not significant result. And so we have a very simple APA style conclusion. Then there's another practice problem, which is one where you'll actually see the math done out by hand on paper. To give you another example of that, and this one is going to be significant. And so it's going to walk you through another example all the way to the end with our Q's and the eta squared and a conclusion. So I know this is a lot. I know it's difficult. I know it's new. Take your time with this. Do the practice problems. Watch the video. Do the homework. And let me know if you have any questions moving forward. So thanks, everybody, and I will see you next time.